In the final chapter of this part, and that also makes it the final chapter of the course, chapter 38, we will look at pattern mixture models. Now, pattern mixture models can be used in a variety of ways, and recently quite a bit of additional work has been done around pattern mixture models. I will come to that. Now, one of the ways in which it can be used is to counterbalance, to contrast a selection model. You can start with a selection model. For example, even the ignorable version, so a simple ignorable analysis in more or less of a selection setting, and then see how a pattern mixture model would actually duplicate those results, etc. Or come up with a quite different set of conclusions. What we've seen in the previous chapter 37 is that a pattern mixture model framework also allows you to define an ACMV, which is a missing at random mechanism, but that's not always the case. One doesn't always do that, so we have to be a little careful with that. But as I said, recently quite a lot of work has been done around pattern mixture models, sensitivity analysis for pattern mixture models, and an important recent reference is work by Carpenter, Kenworth, and Roger. What they have done is they've considered a way of using pattern mixture models, and a little bit like in the context of the predictive distribution, keep the model as it is in terms of the observed data, but then change the identifying restrictions, change the predictive distributions around to conform a variety of scenarios that people could consider plausible indeed. Now, the example I'm going to use here is a so-called Vorazol study. It's a study conducted in postmenopausal women with metastatic breast cancer. It's a multicentric study conducted in North America a while ago by Janssen Pharmaceutica. It's a study that we can use for teaching purposes, also because no further follow-up has been given to the component. There are 450 patients, but the main study outcome is actually survival. So it means, by the very nature of a study like that, people do drop out. People do not make it to the end of the study necessarily. So at the end of the study, which took longer, which lasted longer than was actually foreseen in the beginning, one patient was left. So that actually make it, in the beginning, a population-based study, a clinical trial actually, and at the end of the study, it's almost a case study, because a single patient is left indeed. What we are concerned with here is quality of life. It's a score, a sum score, and the total functional living index cancer, the FLIC score, a higher one is a more desirable one, by the way, is the one of interest. Fitting a selection model without giving too much detail gives us time by baseline, time by treatment interaction, time squared by baseline, etc. And why is everything interacting with time? Well, it's change versus baseline, and therefore, at baseline, you really want everything to be zero, because there is no change from baseline at baseline, of course. The treatment effect, there is none in this particular way. And what you see, and this is actually quite useful to consider, is you would expect fitted profiles and observed profiles, and that's it. And there are two treatment arms, but we see not four curves, because that's what it would be, a fitted one for the Vorazol arm, a fitted profile for the megestrol acetate arm, and then the two corresponding observed profiles. No, we see 5, but there are actually 6. Because if you look very carefully, you see that the lowest line, the solid line, actually covers a dashed line underneath. Now, having said that, of course we can look at the fitted profiles, and that's what they are, and they overlap because there is so little treatment effect. But the observed profiles can be considered in different ways. The fitted profile can be considered in different ways. what it would be had all patients been observed at all time. Secondly, the fit but restricted to those times for which measurements are available. And the latter is directly comparable to the observed profile, but the former way may be more meaningful or less meaningful. It depends. It depends on whether you consider values, missing data values, as something that could have been observed still, no matter what. But in the context of patients dying, for example, that's a tricky issue. Because do you consider a value plausible after death or don't you? There are two views, and I'm not taking any position here. It's possible to say, okay, people die, therefore we should make sure that the model doesn't do anything past that time point. Pattern mixture models are very suitable for that because a priori they fit the data over the range of observation. And that's it. Selection models, if you're not careful, they just look over the entire time frame, whether patients have died, yes or no. Of course, you can say if somebody dies, that person dies with a certain probability. And that probability means that even if the probability of dying is 90%, there is a 10% chance of not. So in similar circumstances, out of 200 patients, 20 will still be there, and we're describing those. There are different views possible, in other words. The dropout model that comes with it, look at it in two ways. You would think there is MAR and there is MNAR. Well, been there, done that. We go back to the Diggle and Kenworth model and say, wait a minute, we actually can never be sure about which of the two is right. And, moreover, there is more than one MAR model possible. If you go from a basic first MAR model that has the previous measurement included, so this one, you can improve upon that by going to one where the previous and the current are used. And that's then MNAR. But, of course, you could also extend your MAR model and say, why don't we look at the previous and the one before that? Let's call it the anti-penultimate measurement. And that has an increment and a slope. And of course, sometimes we get a sense that a missing not at random model fits the data better. But that is just because it allows you to look at the difference between two measurements. Now, if you think about it, there are situations where it may be different, but there may be many situations where it doesn't matter so much where you look at an increment as long as you look at an increment. So yesterday and the day before yesterday may be just as good as yesterday or today and tomorrow, for example, or today and yesterday, as long as you have two subsequent measurements. And yes, this second MAR model describes the missingness mechanism significantly better than the first one, and from there it can be shown that the first extension is no longer needed. So what do we learn from this model? It shows that a low score, a low baseline value, and a negative trend increase dropout. And isn't that in line with expectation? So this is a case in point for studying your dropout model very carefully, and arguably that can be done often in a missing at random context. Okay, here we have a quick plot of the profiles for all patients taken together depending on the number of months they were in the study, and here there are the spider plots of the pattern-specific profiles for each of the two treatment arms. Sorry, that was too quick. Now we fit two pattern mixture models. But without using identifying restrictions or anything like that, what we're doing is we assume, for example, a quadratic trend. You see that here, there, actually everywhere. But you let that trend be different from pattern to pattern. In the first one, you have a time by treatment interaction, and then a time by pattern interaction, for example, but only pairwise interactions. In the second model, there's a time by treatment by pattern interaction, and there the profiles start to diverge, start to be different from each other in a wilder fashion than before. So the treatment effect in the selection model was, and I'm just repeating that, 0.58. The first pattern mixture model produces 0.69. Because you have a time by treatment effect, but no time by treatment by pattern effect, there is a simple, single, unambiguous assessment of treatment effect. Here it's different, because if I have a time by treatment by pattern interaction, I can look at it in two ways. If there are, for example, 10 profiles, there are 10 treatment effects, and there are 13 to be precise, so I can look at all of those jointly, and then I have the combined effect, the composite hypothesis. All of these treatment effects are equal to 0. In the second way of looking at it, I basically bring down those time by treatment by pattern effects. I average them into a single treatment effect, and that still is non-significant. But how do you do it then? So all of the treatment effects that I circle now are standard assessments based on either one parameter that's in the model or 13 parameters that are all in the model and for which I have a joint hypothesis. The last one is based on a different number, on a different quantity which is actually a nonlinear function of model parameters. What model parameters? Well, the beta LTs are the treatment effects in each one of the parameters separately. The pi's are the probabilities with which each of the patterns occur, so this is a weighted average. But of course, both the betas and the pi's are parameters estimated, and therefore they are uncertain. And using a delta method calculation, I get the variance of that new parameter, or that new set of parameters, because there are as many as I'm willing to look at, using a delta method application indeed. Okay, now how should we best fit pattern mixture models? What we did now is simple quadratic functions over the observation time, and that's easy to do. It's making the model simple enough. That's what we do. Is quadratic simple? Well, we can agree or disagree on that. The thing is that these models, if you would extrapolate them, would do the weirdest things. Look at that. The fact that the profiles tend to go up and then come down and then drop out is fine, but you cannot really use them for extrapolation. Why is it fine if they behave this way? Well, as long as the score gets higher, it's better, but you typically see in all of the patterns, the moment people start to deteriorate, it's over. Don't extrapolate. Maybe it's not necessary to extrapolate and then it's fine, but if you extrapolate, you can even get completely implausible values in ranges where you don't want to go. You can also do identifying restrictions, and we know already from a previous chapter ACMV. What is ACMV again? Well, the predictive distribution should not depend on the pattern. It's going to be the same in every pattern. Of course, given the past measurements, it doesn't mean that everybody is evolving exactly the same after dropout. No. That will depend on the profile observed for them up to then, but not further on anything else. CCMV is complete case missing values. Whatever is missing, you borrow from the completers. And neighboring case missing values is the entire distribution or the distribution of what is missing given what's observed you get from the nearest neighbor, and only from the nearest neighbor, not from the other patterns that are also more complete than this pattern. For example, if you have 3 measurements and number 4 is missing, you can borrow number 4 from the pattern with 4 measurements, the neighboring pattern. But also the pattern with 5 measurements has number 4, and the pattern with 6 measurements has number 4, etc. Okay, these are all possibilities, and of course all of those are ways to identify the predictive distribution, and therefore they cannot be distinguished from each other in terms of likelihood. They're just tools for sensitivity analysis. Simple models per pattern, or pattern as a covariate. Pattern as a covariate is what we just did with our quadratics, and simple model per patterns is keep your models indeed simple enough. Okay, the identifying restrictions, as we said, for complete case, for CCMV, we go to that guy, and we go to that guy, and that's how we identify. That's CCMV. ACMV, or let me do NCMV first. This measurement missing is identified from that guy. But then it's over, of course, and the last one would be identified from the completers nevertheless. Same here. That one would be identified from the completers. ACMV, for this value, would go to a combination of this one and that one at the same time. So in other words, this one is an interesting one. The one that I've now, the purple block now is a missing measurement, of course. NCMV goes to pattern 2. CCMV goes to pattern 3. And ACMV goes to a combination of 2 and 3. That's a way to think about it. Everything else, it's a simple setting, is identified from the completers here. But it's a good exercise to work out what this now would be for 4 measurements, 5 measurements, 6 measurements, etc. If we do this, we start with a model fitted to the data that we have available. Then we could fit a model to the extended data, but how would we do that? There are several ways of doing it, but a simple way is using multiple imputation. Based on the model you have, based on the identifying restrictions that you use, you can sample from those predictive distribution and then refit the model, for example. That's one possibility of doing it. You would get a fit here. If you use pattern as a covariate, what would that mean? You basically say, okay, I have treatment, I have time, I have a baseline, but I also have pattern, and I use that as an additional covariate. And the beauty of it is, I can let all effects, many effects, a subset of the effects, etc., depend on the pattern. Excuse me, depend on the pattern indeed. It's entirely up to us. For example, the variance components here do not depend on the pattern, but if necessary, I can make that happen indeed. If you look at ACMV, which is MAR, you do see that the extrapolation, and that's what it's now about. We want to extrapolate, of course. We see that ACMV does do something reasonable, but using pattern as a covariate and things like that may come up with entirely implausible predictions. So we have to be very careful with something like that, indeed. And that's what I would say. Identifying restrictions, yes, they can be used for extrapolation, but everything else be very, very careful about. Okay. So, in conclusion, we conclude that, as we have said before, pattern mixture models can be used in a variety of ways. They allow ACMV, they allow non-future dependence, they allow for the general mechanism as well, as we have said before. And as an overall conclusion about missing data, in the previous part, not in the current part, but in the previous part, and these are really the overall concluding remarks, we set the simple methods, CC, LOCF, single imputation, they're biased, they're inefficient, a combination of the two, don't Museum of Statistical Science. That's where they belong. Missing at random, with, of course, direct likelihood, direct Bayesian analysis, weighted estimating equations, multiple imputation, doubly robust methods are in the meantime a very rich toolkit with an ever-expanding set of software tools, even in standard commercial software, to make them happen, to fit them to real sets of data indeed. And then, as this particular part, chapter 35 up to now, has indicated, missing at random cannot be ruled out. And it's not something like, okay, we should think about it and maybe then test. No, you will never be sure. So it's possible, it's always possible, no matter what you have done already, that the true mechanism will be still different from what you have done. And that's where you need to do a form of sensitivity analysis. Now about that, I think it's fair to say, it's not so important what sensitivity analysis you do. Of course, it's important, but it's even more important that you do sensitivity analysis, that one, you are aware of sensitivity analysis tools, and two, they're properly used in function of the research question that you have. Because there almost never is a situation where you can safely say, we are now sure about what the missing data mechanism is. I think it's realistic to say you cannot. That's not really possible. Okay, that brings me to the end of chapter 38, and this particular page is chapter 39. It also brings me to the end of the course, and therefore to the end of this lecture. Thank you.